So I want to tell you today about resolution proof system. And as I mentioned, it was invented or suggested by Davis and Putnam, Martin Davis and Hilary Putnam, in 1960. Hilary Putnam just passed away at the age of 90 just a week ago, so I can dedicate this to him. A really funny guy. I mean, I met him about 10 years ago. It was really amusing to talk to him. Those who don't know, he was a philosopher of mind at Harvard and did lots of things between logic, mathematics, and philosophy. So I'll remind you some things I said last time about general proof systems, and because I want to talk about some properties of resolution, so I'll define it. And I want to talk about properties of this proof system, and I'll put it in the context of general proof systems. In particular, two important ones are automatizability and feasible interpolation. And both are important. This is in an obvious way, this in a less obvious way to proving lower bounds. And I also want to, of course, prove lower bounds, which is the main thing I really want to do on this proof system for some natural tautologies. So I'll define natural tautologies and prove to you some lower bounds. So let me just recall a few things we talked about last time, and then we'll get to this, which is the main thing. So I want to spend about 10 minutes on the background and also define these notions which I didn't formally define last time. So proof system, and we are just always talking about propositional proof systems. So the definition of Cook and Rekar was very general. I mean, a proof system is anything that has a polynomial time verification. So I defined it for the language of tautologies, which is the only language we will be really caring about in proof systems, but you can define it for any language L. So V, so polynomial time machine, Turing machine. V is a proof system for L, for a language L, if it just accepts all strings in all proofs for strings in L and rejects all potential hypothetical proofs for strings not in L, if X is in L, if and only if. Well, let me call it phi because that's how I called it last time. It's it's an element in this language, but we will think of it as a formula. If and only if there exists a pi, that V of phi is 1. And then we think of pi as a proof of phi. And what's important is that the machine is polynomial time in both inputs. So the proof may be long, but verifying it is polynomial time in the length of the proof. Okay, and we said that what we are interested in is proof length. That's a major object of study here. So proof length. So a proof system V here is L of n bounded if for every so, and I'll say L for us will be the propositional tautologies or propositional contradictions, even though this definition is general. V is L of n bounded if proofs, they're always short proofs, short in the sense that their length is bounded by this function of the given input or tautology. If for every phi in L there exists a pi such that V of phi pi is 1, and the length of pi is at most L, the length of phi. Okay, so the main question we talked about is, are there polynomially bounded proof systems? And we mentioned this theorem of Cook and Rachau. Poly-bounded V if and only if NP equals co-NP. All right, so you can think of trying to prove lower bounds for various proof systems is trying to refute this equation in stages. Okay. There's one obvious question to ask about the proof system, and this will be relevant in particular for resolution, is, okay, suppose there exists a proof. How long does it take to find it? Okay. So finding proofs is a very important task, I mean, for mathematicians in particular. I mean, usually when we start trying to prove a theorem, we believe that we will eventually write it and it will fit in 20 pages, or maybe in the case of some people, 50 pages or 100 pages. But anyway, we know that it will be of a certain length. And the question is, given that this is the size of the proof, how long, as a function of the size of the proof, does it take to find? So this is a question of automatizability. You would like to have, I mean, ideally, for a proof system, an algorithm that if a short proof exists in that system, then it is easy to find in some sense. So automatizability we say that V is, so again, we need a parameter for the, you should think of the time it takes to find a short proof or find the proof. So we said that V is, well, maybe I can use again L of n, or maybe I'll say S of n. Automatizable if whenever there is a proof of a certain length, then there is an algorithm. So if there is an algorithm that, given that there is a proof of a certain length, it finds it in time, this in the length of the shortest proof. So if there exists an S of n time algorithm such that for every phi, if V of phi pi, every phi and pi, V of phi pi is 1, then also V of phi and A of phi, I should say, is 1. So A can produce a proof and the running time is bounded by, I should say, so algorithm A runs in time S in this total proof length. So I'm not sure how to write it in the best way. A gets only phi as input, but runs in time S of phi and pi. Okay, so it just captures the time to find short proofs. And I've given you a list of, so the definition is clear. I mean, if there's a short proof, there's an algorithm which is within the same time, or, well, function S of the length of the proof finds another proof, maybe. So, we continue here. What we want, I mean, ideally, is, poly time automatizable proof systems. V. Well, what does it mean we want? I mean, there is here you get to the obvious trade-off between provability and automatizability. You may expect, and this is, from all we know and from the intuition, I guess, is if you have a very weak proof system, then it is more likely to be automatizable. But unfortunately, if it's a weak proof system, probably the proof length will be long, and in that, to find long proofs is easier in polynomial time in their length. So there is a trade-off between the expressibility or the proof power of a proof system and its automatizability. It's a fact. I mean, it's an empirical fact. The stronger the proof system, the less we expect it to be efficiently automatizable. And just to give you examples of proof systems that we discussed last time that we know are automatizable, which are not so weak, and it's really interesting. So then we'll challenge that proof system. Proof system, the polynomial calculus proof system. Proof systems, so both are proof systems that work with polynomial equations, and the sum of squares. Sum of square systems are all polynomial time automatizable. The first two follows just because of linear algebra. To solve system of linear equations, it's in polynomial time, and the last one, sum of squares, follows because semi-definite programs are solvable in polynomial time. So on the one hand, I said that these are strong proof systems. They are strong, but there is a weakness in them, and I discussed it last time, is that we consider here only the most naive and stupid representation of polynomials, namely as a list of their coefficients. So in that sense, actually, proof length is not so short here. It's just, anyway, proof lengths are not really short, even if you can, even though they seem powerful and they are extremely useful, this statement is not that shocking because we are treating polynomials just as a list of coefficients. If you replace these proof systems, that would be extremely interesting by the same type of logic, only that you represented polynomials by circuits, then I doubt very much it would be automatizable.
But is polynomial time, then you do have, right? Like if you have getting sets, then you can do linear algebra.
Yeah, for these.
For the
Nostalgia. Right. Yeah, so probably, yeah?
If there's a sparse polynomial that solves it, so it wouldn't find
Yeah, if it's sparse, but, so sparse. So if you're working with sparse polynomials and you demand that it's sparse, then the proof system is, is stronger, or you may expect. So you may expect shorter proofs, but then. Okay, which direction am I going? So what are you trying to? It will not. If you're just working with.
Proof,
yeah.
You wouldn't necessarily find it in times that it's polynomial in the sparseness. Like, times it's polynomial in like.
Yeah, that's right. So exactly. Yeah. Sorry. So I understand what you're asking. It may be that the proof here is just working with sparse polynomials, but this time will be time in the dense representation. Yeah. Yeah. Anyway, so we have this, and I'm mentioning this because I want to discuss the automatizability of resolution. Anyway, clearly, if you have a proof system which is polynomial time automatizable, and you have lower bound for a computational problem associated with your, with your tautology, then you have a lower bound on the proof length. I mean, basically here, both in polynomial time automatizable proof systems, the length of proofs and the time to find the proofs is the same. So if you have a computational lower bound, you also have a proof length lower bound. Okay, so that's automatizability. The other notion that questions. Is anybody baffled? Okay. The last notion I wanted to define is that of feasible interpolation. And this, so while automatizability talks about finding proofs for every tautology quickly, this talks only about certain types of proofs, certain types of tautologies. So the type of tautologies that we are talking about are predictions are of the form xz or p1 yz. So these are sets of variables, x, y, z, disjoint sets of variables. And it's clear that if phi is a contradiction, then for every fixed z, well, let's call it z naught, for every fixed z naught, either phi 0 of x z naught is a contradiction, or phi 1 of y z naught is a contradiction. Right, so this leads to a computational question. I give you z naught and I'm asking you, is it a contradiction or is the other one a contradiction? It's a computational question. Yes, so I'm just, phi is known, phi is given. And now I give you this binary string, an assignment to the variable z, and I ask you, does it render phi 0 as a contradiction or phi 1 as a contradiction? One of them must be, right, because they are disjoint sets of variables. So it's a computational question. The question is, what is the computational complexity of this question? And the feasibility, for contradiction, it's an or, I think. Or it's an and. Thanks. It's an and. Yeah, very good. Okay, so for different proof systems, you want to ask the question for this kind of tautologies or contradiction, what's the complexity of this problem? And well, I'm not going to define again S of n, I'll just talk about polynomial time. So we say that V has a feasible interpolation property if there exists an algorithm A, so that whenever it is present, maybe I'll call this different algorithm B. Algorithm B, which is a polytime Turing machine, such that on every phi of this form, so phi 0, phi 1, and z naught, correctly which of phi 0 is a contradiction. Okay, of course it may be that both are contradictions. It's not really a function, it's a, it's a relation. If both are contradictions, it can answer any one, otherwise it answer correctly. So again, this automatizability, this is another property of proof systems, and it should get harder to satisfy the stronger the proof system is. It is easy to see that it's a refinement of the automatizability system, so a very simple fact which you can check just to see that you understand the definition is that if V is automatizable, then V has a feasible interpolation. But not necessarily vice versa. And okay. Do I want to say any more about this, or we start with resolution? So we know some proof systems with feasible interpolation. I mentioned that cutting planes has some form of feasible interpolation. It's not exactly polynomial time. There were these weird real gates involved, and I'm not going to repeat it now, but we will see that resolution has a feasible interpolation. In fact, has a feasible interpolation of a strong type, and which helps for lower bounds. Okay. But maybe I should state, so one result of, without writing it down, just one result of Kreitzer and Putnam to show you that we don't expect feasible interpolation for strong systems, is that, I can write it down. Theorem, Kreitzer, and Putnam. If Frege, the Frege proof system, has polynomial interpolation, then factoring is in P. Okay. You can ask me later. I can give you a hint how this is proved. It's very simple.
Polynomial means the physical interpolation.
Feasible interpolation. Thanks. Okay, so, but it will turn out that the resolution does have. What? Well, you should think about it. I mean, you can find proofs, and well.
So in some proofs, like the coloring versus clip versus coloring,
Mm-hmm.
you don't actually have to find the feasible interpolation, right?
You don't have to find the particle.
Whether there is a clip.
Yeah.
You have an argument showing that there is always either a clip or
Yeah, but because of the structure of the tautology, you are forced to find a proof which proves either one. That's more or less. You find the proof, then you set z0, you set the variables of z0, and you know which one.
this is really an end?
Yeah, it's an end. So if the conjunction is a contradiction, then one of them. If they are not,
Both of them have to be false.
No, but I'm trying to understand something you said last. So last time we had the coloring versus.
yeah, we will go back to coloring verse. So if you want to,
And then
yeah.
the problem with the proof system was that they were trying to understand whether
Yeah, that's right. A coloring or a click.
Or a click. And morally, you don't have to do this. Morally, there is like an argument that doesn't have to.
That's right. But in the propositional case, there is no room for an argument that wouldn't do this. You will see it when we discuss the feasible interpolation for resolution. But in the case of for systems, well, let me not go into this. It's a simple fact.
But in the feasible interpolation, you want the Turing machine to be all the time in the formulas or in the.
It's always in the length of the. So in both cases, it's in the length of the proof, right?
It's not clear that.
It's in
the interpolation, it's not clear because you don't need to come up with a proof. You just need to say which is true.
Yeah, but the running time is polynomial in the length of the proof. That's what I mean. Yeah.
Maybe it's
when I define the feasible interpolation, it's the running time of the Turing machine, which has to tell you which is which, has to run in time polynomial in the length of the proof. Okay.
So B takes as input phi.
Yeah, phi, you
Phi
know.
1 and phi 2.
Yeah, the contradiction and an assignment.
Oh, okay. Contradiction and assignment.
Yeah. It's really the contradiction is given, and then for every assignment it's. Okay, let me go back to resolution and start doing some proofs. I'm not going to extend this to another lecture, so I want to make sure I do something. So I will denote always phi these are functions or formulas on x1 to xn. These are the variables, these are the given formulas. And for us, from now on, they will be clauses. It will turn out that it will be useful not to always think about them as clauses, but you should think of them for now on as clauses. So each AI is something like x7 or x9 complement or x. Okay? You are back to this. It still bothers you about it? Like,
No, now I understand that you cheat. It's okay.
well, that's normal. Okay, so think of these as clauses, and we are going to, while we have this general definition of a proof system, which is just a Turing machine, from now on we will think of the normal deductive type of proof systems in which we are just following a chain of formulas, and each one is derived from previous ones using a simple rule. And I'll tell you what is the rule in the case of resolution. So let me just say how a deductive proof for this in general looks like. The pi we will think about will be C1, C2, CT, which is a contradiction, and these ones will be A1, A2. So we start from the axioms, and then each CI is derived from some CJ and CK. CI is a legal deductive rule, legal deduction. This is in general for proof systems that we look at, and of course J and K are less than I. So you deduce from previous formulas 2 or 5 or something like that. And what is the rule? What is the resolution rule? It has only one deduction rule, and it's very simple. So since we are just dealing with clauses, it's just disjunction of variables. Suppose you have two clauses, let me call them D or X. So you have a clause in which X appears, and you have another clause in which x bar appears. And legal deduction is always of the form, if anything I assume is satisfiable, then what I'm deducing is satisfiable. That's a sound rule. So also here, if both of these were satisfiable, right, x cannot be both true and false, so one of the D and E must be satisfiable, so you can deduce this. Okay, that's the resolution rule. Clearly it's sound, and it turns out that it's, so resolution is sound, and it's also complete. Every refutation can be refuted in this way via resolution. That's a simple exercise. Okay, good. So now we want to talk about some results about the power of resolution. I'm not going to tell you the history. It's really interesting. It's very important. It's one of the main, resolution is one of the main tools in verification systems. You want to verify that some hardware design you have, or some protocol, or some, I don't know, maybe some cases software piece is working correctly. It satisfies the specifications. You make it propositional. You make all the claims about the fact that things are working correctly using propositional variables, which are supposed to capture all possible scenarios. And then you write this, what would hopefully be a tautology, that it works always. And you try to prove it. You want an automated prover, and the question is, what proof system are you going to use? This is the method of choice for a huge number of applications. So it's really important to understand this proof system. It's also, it also turns out to be projects in the 60s trying to really automate theorem proving, like theorems in mathematics. And again, you can, some theorems at least, you can state propositionally and try to prove them automatically. And again, proof systems, there are lots of projects in which they try to prove elementary combinatorial statements, elementary number theory statements automatically using resolution. Okay, so it's very important to understand it, and to understand both how how short proofs can be, and how can you automate this finding such proofs. Okay, so let me go to some. Maybe I'll show some resolution proof. Just let me. I don't know. X or Z, X bar, or Z. So this is a contradiction. How do you prove it? You can resolve this on resolve this on the Z variable, so you get here X bar or Y. You can resolve this on the Z variable, so you get X or Y. And then you can resolve these on the X variable, and you get here Y. And what else can you do? You can, but I don't want to do it faster. Okay. Of course, you can do it faster. So you can do this, for example, you probably know Y also, so you can get here, I resolve this on the Z variable, so I get X bar or Y bar. I can resolve this on the Z variable, and I get here, I guess, X or Y bar. I can resolve these to get, on the X variable, to get Y bar, and I resolve these two on the Y variable, and get it. Okay? So that's an example. Okay, so now let me state some tautologies and what we know about them. And then we will prove them, or prove some of them. questions so far? Yeah.
Is anything known if you put some kind of computational kinds of constraints on the nature of the proof? Like you can't look back further than some fixed. You mentioned a couple times that the deductions can't reach back too far.
Yeah. No, the deductions can go anywhere to the back. I mean, to the history. Anything you
They
have.
can go anywhere there is.
Yeah, anywhere. Yeah.
Okay, so what if you don't really allow that? I mean, does that make any sense?
It does. It does. It makes a lot of sense. I'm not going into some. Yeah, maybe let me formally define some the complexities, and then I'll answer your question. So we'll deal here with, even though proof length is the main thing we want to address, I'll mention two parameters, and then I'll answer you. So we will be interested for any tautology, for any contradiction in two length parameters. The size, the length of the proof for pi is just the minimum resolution proof length. That's the normal thing, just what's the length of the sequence. And for ST, so this T is for tree, so it's a minimum tree-like resolution. Here, this is a normal resolution proof. The length of it, you can make it straight line. It's like a circuit, and you can count how many nodes are here. Tree-like proofs, which were historically the first thing for which there were lower bounds, are exactly those when you open this circuit into a formula. When you here, I use this. Maybe here I didn't use anything twice. If you use anything twice, but maybe this is a formula already. Yeah, that's a formula. So that's a tree-like proof. But anyway, if you derive some clause and you want to use it more than once, you have to derive it again. Just like in formula, you want to use something you computed again, you have to compute it again. So this is a weaker parameter, and we will talk about it when we discuss automatizability. So I do want to keep it, but people.
Other way around.
Thanks. Other way around. Thanks. But you can discuss other parameters of proof systems, and some of them are important, like, something that in the direction you mentioned, the space. So you are collecting these clauses, right? You are just accumulating the clauses that you derive from the axiom clauses. And suppose your memory is bounded. What happens then? So you cannot, it's not necessarily not going back, but you decide how much you keep and how much. When space is bounded, time increases. There are beautiful works on trade-offs between time and space. Some recent ones very strong due to Chris Beck and Russell Impagliazzo and Paul Beam. And I'm not going to talk about it. So there are other parameters which are important that I'm not going to discuss. I'm just going to discuss proof length and proof length when the proof is a tree. Okay. So now I want to talk about the tautologies. And PHP. So this I already discussed last time. Here you have variables xij. I goes between 1 and m, and j goes between 1 and n is less than m. And the tautology is basically, so it can be expressed in clauses. For every I, we have the disjunction xij, and for every j, and for every I different than I prime, we have the disjunction xi j or xi prime. So the first says that there is a 1 in every row. The second says that there are no two 1s in every column. So it's a collection of disjunctions. They are contradictory. What's the shortest proof here? So maybe I'll write some theorems here. The main theorem that was the first breakthrough giving lower bounds for resolution proofs is by Haken. The size of PHP and n plus 1 is exponential. Right, exponentially n. Okay, so there are exponential lower bounds, and we'll see a proof of this. Okay. I should just mention, even though I'm not going to go there and it's beyond the proof techniques I'll talk about, is that you can ask this question of the pigeonhole principle. You can ask the weak pigeonhole principle. What's the weak pigeonhole principle? So suppose I give you 2 n pigeons, and I say they don't fit into n holes. That's an easier thing to prove, right? I mean, it's not harder. It's a bigger contradiction, right? If I give you 2 to the n pigeons, it's just, what's the proof length in that case? Actually, it's really interesting that Tony Pitassi observed that if you have many pigeons, let's say you have 2 to the root n pigeons, then this is at most exponentially, roughly. If you have many pigeons, you know it's easier to prove a law by sub-exponential. And the question of what's happening and whether this can go down to a polynomial, right? You don't have to use all the axioms. You use whatever axioms you want, right? We don't write all the axioms in the proof. We just use those we want. And a very important theorem of Ran, if you have a month to kill, you can go and study this paper. And is that, you cannot improve this basically. And infinity. Okay. Razborov had extensions and some improvements of the bounds, but that's the basic thing. It doesn't go down to a polynomial. It remains exponential. But I will not talk about this. Okay, so let me tell you about other cool tautologies, Zeitin tautologies. They go with a graph, Zeitin. I introduced them in the 60s and proved already some lower bounds on some restricted forms of resolution. So this is a tautology associated with a graph. So we'll assume that G is a graph. It has n, so V is n, and it's odd for simplicity. Let's graph on an odd number of vertices. The variables here are associated with the edges. For every edge, we have a variable. And the tautology claims that I'll write it as not as disjunctions, but as parities, but you can move to disjunctions. Let's say let's say it's D regular, or the degree is at most D. What are the conditions for every I, for every vertex? For every vertex, you have the condition that the exclusive OR of the variables on the edges touching I is 1. Okay? So the parity on I in E, right? All edges that are touching I, XE is 1. So you have this for every I. So it's basically a system of linear equations. This system of linear equations is unsatisfiable. Why? Why is it not satisfiable? Because it's odd. Yeah, if you add up all the equations on the right-hand side, mod 2, on the right-hand side you get 1. On the left-hand side you get 0 because every edge has 2 endpoints. Right? So it's obviously a contradiction. If you care about writing it as a tautology, as disjunction, you write every parity, let's say the degree is d, then there will be 2 to the d minus 1 disjunctions that encode this parity statement. So you can write every parity as a set, as the end of O's, basically. So it's n times 2 to the d disjunctions. So if you want this tautology to be useful, you better take d to be small. You don't want an exponential number of clauses here. Just take d to be a constant. And what's the theorem here? So this is so after Haken's work, some other lower bounds followed, and one of the first ones that was by Urquhart. Is about 87. Size of Zeitin tautology G is exponential in n for every expander. If G is an expander graph, then proving this contradiction requires an exponential number of clauses in resolution. Okay? We'll see the proof of this. And the third one, is simply a random 3-sat. And you can put random k-sat if you want. So what are the axioms in this in the random 3-sat? It's just a random collection of 3 clauses, right? So pick A1, A2, let's say 10n. We are on n variables, so we have x1 up to xn are our variables. Pick 10n clauses at random. So each AI is, so AI is xi1 or n epsilon 1, xi2, epsilon 2, or xi3, epsilon 3. These epsilons means it's negated or not negated. Arbitrarily at random, you pick the indices and the negations at random. Pick 10n of these. What do we know about this? We know that the threshold for satisfiability is around 5.3. In other words, with extremely high probability, this is a contradiction. It's interesting to prove low bounds on contradictions which are contradictions. I mean, if this is satisfiable, low bounds are really easy to prove because there are no proofs at all. Anyway, so with high probability, this is a contradiction. And what Schwatter and Semeredy proved proved is that with high probability over this choice, size of random 3-sat is, and we'll see a proof of this. Now, the last contradiction or tautology that I want to mention, I mentioned it already last time, so I won't write it down, but I guess this follows from Krajcek and also Razborov, although I think, but I'm not sure who wrote this. It's, I guess, Ran, it's really independent, even though I think I have a reference for Krajcek. I'm not telling you. Is that the click versus coloring. So the size of this tautology is exponential in n to the omega of 1. Exponential lower bounds on this, which I defined last time. We will get to define it later. But I think that this there's one method here, which in these original proofs follows from Haken's method called the bottleneck method, and uses random restrictions. I'll show you a different proof, and this follows from the feasible interpolation of resolution. Okay, which I hopefully will also show you. So I want to, yeah.
Regarding the random crystal, does it become easier if I draw more clauses?
Well, you get already an exponential lower bound, so it shouldn't.
No, but maybe easier.
Does it easier? Yeah, of course. So if you, for example, it's known that it's really easy to show that there is a polynomial type resolution proof if you draw n squared clauses. And the best known, I think for resolution, if you draw a little bit more than n to the 1.5 clauses, it's easy. I know it's easy. There's a polynomial type proof. I'm not sure it's resolution. I don't know, Ran, you remember? Just if you have a random start with many clauses, n to the 1.5 clauses, then it can be refuted in polynomial time. I'm not sure it's a resolution proof, but what?
I don't think it's
It's not, maybe it's not, but I think it may be. But if you draw n squared, then you can even do it with resolution. Yeah, so you're right, it becomes easier. So let me tell you a few things about the first method, what I'm going to do, and then we take a break. So I want to tell you the proof of the first three theorems. And the proof I'll tell you, they all fall together from a paper of Eli Ben-Sasson and myself. And they follow very simply from what we call the width method. So it's a very different method, Haken's method. And it's really simple. Those of you who would try to read the original papers, this is relatively clean. This one and the original one, Haken's one, are a real mess. I mean, they are extremely long, extremely complicated, and it's hard to know exactly what's going on, except that you get the result. I mean, there are obvious ideas there, and they articulate them, but still, it's really the first three. I mean, no, this is off the chart. These two are, so this, and this. The three exponential lower bounds. Okay, so it's going to go through the width method. And there are two nice things about, I love this paper, it's mine, but is that it articulates another parameter of resolution proofs. It's an obvious parameter, but this parameter is simply the width of the largest clause that appears in the proof. Maybe I'll write it. The minimum over all proofs, resolution proofs of for phi, is the minimum, the maximum. Ci is in pi, the number of variables in Ci. So it just, you try to find the proof in which all the clauses are short, are narrow. Actually, this paper is called Short Proofs Are Narrow, and what it proves is the following two statements. It basically says that if you have a short proof, then you have maybe a different proof, which is narrow, which is all the clauses are short. So I'll state it, and I'll tell you some consequences of this, and then we'll take a break. Okay, so I don't want to bother now with what may be called, which we do call, I guess, W0. This is just maximum of AI. So we are going to prove upper bounds on, we are going to prove lower bounds on this. We are going to show that every proof must have big clause in them. Now, if the original axioms already have long clauses, then it's not really interesting. I mean, it's just the axioms that are given are already wide. So you don't want to bother with it. Well, it's not a problem here, because these are 3 clauses. It's not a problem here if you take D regular expanders and D is a constant, like 3, so it's not a problem here. In the pigeonhole principle, it's a problem, but there are ways of making the pigeonhole principle. You can write them in a way that the axioms are also 3. I mean, in general, it's clear that you can do it in some sense because of Cook's theorem. You can make every tautology a tautology of clauses of length 3. But anyway, so I'm not going to bother with it. Always assume that this kind of thing, for our purposes, is a constant. So I don't want to even think about it. We just care about tautologies that have constant length axioms. And what are we proving? We are proving the following statement. So what short proofs are narrow. Here's the main theorem that is driving the lower bounds, is that for every phi log so if you have a short tree-like resolution proof, then you can find another tree-like resolution proof in which but anyway, a resolution proof in which the width is logarithmic in the original size. That's for if you have a tree-like resolution proof. And if you have just a resolution proof, then the upper bound is weaker. You get something that looks like this, n log s. So you get something that square root of the number of variables times the length of the shortest resolution proof. What I want you to remember for both, I hope I'll have time to show you one of them. I mean, that's easier. But they are both the same, and they both follow from a paper in polynomial calculus of Clegg in Pagliazzo, Edmondson in Pagliazzo. It's the same idea applied to resolution. So it's really simple, really, really simple. So 2 things to observe about this. One is that if you can prove, so how does it prove lower bounds? If you can prove lower bounds on width because of this relationship, then you can prove lower bounds on size. And in particular, if you prove that omega of n, then this implies not only, so of course it implies that the tree size is n. It is exponential in n, right? It's just log. But also it proves that this is exponential. So this implies that s of phi right? But you can do the calculation. Yeah. So you can get exponential lower bounds just on size just from proving linear lower bounds on width. And that's what we'll do, and that's how all these things will follow. So one key fact is that you work with, as you'll see, a much weaker, simpler parameter to work with, this closed size. And you need to prove linear lower bounds. Another thing that will become apparent in the proof is that it sort of highlights expansion, in some sense, expansion in the set of axioms as the key to proving resolution lower bound. Lots of resolution lower bounds are proved, and in fact, this was extended to other proof systems. Expansion in the proof system, expansion in the set of axioms, which you have to define, implies that it's hard to prove in simple proof systems. So that's something that came out of this. And the last thing I want to mention is an obvious consequence of this to automatizability. So what's the obvious consequence? Well, suppose you know that there is a short proof. Suppose you know, yes, that there is a short proof. Then there is a narrow proof, right? A narrow proof has only small clauses. How can you find such a proof? Well, try all clauses up to this, just enumerate them and try to see which are implied by the axioms. You know that, they should lead you to a contradiction. So, so that's obvious. So, so a corollary is that tree like resolution has quasi-polynomial interpolation, right? I mean, about n to the log n interpolation. Just by this, you just try all clauses up to log. And resolution has sub-exponential, or roughly 2 to the root n. Sorry, not interpolation, automatization. Don't know why I said, automatization. Automatization. We don't know that any of these results is optimal. Maybe resolution has a polynomial time automatization. Maybe it's fully automatizable. It's unlikely. Razborov and Aleknovich proved that this is tight under some assumption in fixed parameter complexity. So probably you cannot beat that. This may be far off the truth. Maybe this can be improved significantly. So we don't know. So this, but anyway, resolution can be non-trivially automatizable by this as a consequence of this very simple result. Okay, so let's take questions first. All right, so let's take a 5-minute break. All right. Okay, so I'm going to delay the proof of this to later. I want to show you how to use, I want to prove a lower bound. Okay, so first. Okay, so now I'm going to show you how simple all these lower bounds are that I erased from the board. Are the exponential lower bounds on resolution proofs for all these 3 tautologies. Okay, so.
So are you showing the theorem, or?
Yeah, I'm proving the theorems that I erased, these 3 theorems.
This theorem? Or?
No, that this requires exponential size, this requires it. I will, later.
Oh, okay.
Yeah. I will tell you this later. I want to get rid of before. I want to make sure you see a resolution proof lower bound. And it's short. It's, then I'll tell you about this, and I'll tell you about feasible interpolation. Okay? What?
It's a short proof that proves so long.
Yes, it's a short proof that proofs are long. Which you have to start thinking about the proof systems we are using in life. It's not resolution. So what do you want to do? You want to prove that, you want to show that any resolution proof of this kind of tautologies require a clause somewhere in the proof, a clause which is linear length. Okay, so we'll do it in generality. Let's assume that we have this initial tautology, And I want to define two properties of this tautology that will imply a lower bound on the width. Right? Again, width is the only thing we need to prove a lower bound for. So I want to say first what it means for C to be R robust. R robust is basically that if you look at subsets of the axioms that are of size R you would like to make as large as possible, subsets of the axioms of size R, they are satisfiable. What does it mean? It means that, this is an honest contradiction. It's not, a very small contradiction plus a bunch of junk that you don't really need to use, right? So R robust, if for every subset I of M, I at most R, let me call it A sub I, which is just A sub I and I, is satisfiable. Okay? So it's like R to be big. Okay, that's R robust, and what the other one is that it's R expanding. So both these properties will drive lower bounds, and then it will be essentially a triviality to check them for this with a parameter R, which is constant times M. So what is R expanding? For this, we are going to, I told you that the axioms are short, maybe they are on 3 variables, but anyway, they are on some subsets. So let's SI denote the support of AI, just the variables that the I's clause depend on, or the I's function depends on. Okay, and then you want to draw, I want to define the boundary of phi. So what's the boundary of subsets? It's just a hypergraph. So you have this family of sets now. I don't care what function is. It's a family of sets. Here we have M, here we have N again. These are the variables, so it's not this picture. Sets of variables, so it's just a hypergraph. Okay? On the vertex set N. And what is the boundary of a set? So we look here at a set of rows I. And what we care about, so it's a bunch of edges in our hypergraph, and the boundary of this set is simply the vertices belong to exactly one set, exactly one. They are on the boundary in this set. Okay, so let's write it down. So phi of I is the collection of J in N, and J belongs to a unique AI, I and I. So this is unique. Okay? And now our expanding is if every set which is not too big has a large boundary. So our expanding, if for every I in M, I at most R, the boundary of I is a constant times the size of I. Okay, some constant fraction of the number of sets is actually isolated vertices. Okay, let's just check one, so first of all, I put the same R in both. You can put different parameters, but the minimum of them would imply the lower bound, so I put the same parameter, R. Let's check that citing tautologies satisfies both robustness and expansion for expanding graph with parameter R, which is linear in N. Okay, robustness. This system of equations is unsatisfiable, right? But even if I remove any one of them, right? Any one of them, then it becomes satisfiable. Yeah, so that's really easy. It's robust with N minus 1. Okay, why is it expanding? Well, here, what are the sets? The sets are so this is n also here. Well, I guess it's reversed. The matrix is reversed. But basically, we are looking at a set of equations. So a subset I of equations. Set of I of equations is a subset of the vertices. We have a subset of the vertices. And we look at the edges touching them. So what is the boundary? The boundary is exactly the edges between these sets and its complement. Right? What is an expander? An expander is one for which, this set is large as long as we don't go over half the vertices. Right? So you can really see that this is so maybe I should write it here as an example of something you can verify about the others is that this Zeithin tautology, if G is expanding, then TTG is omega n robust and omega n expanding. Right? So it's very easy to verify these properties for lots of tautologies, and once you have it, you get lower bounds. So how do you get lower bounds? So I want to prove to you that if you have, so the main theorem, which is also really easy, but it requires a few steps, so this is from our paper. If phi is R robust and R expanding, then width of phi is a constant times R. And so we get these exponential lower bounds directly from. What's the proof? We're going to use very simple properties of the resolution proof systems, and in fact, you'll see the proof of this theorem does not care at all about what the resolution proof is. It just cares about the fact that the lines in the proof are clauses. All implications, they can be arbitrary sound implications, can be semantic. In particular, the axioms can be arbitrary formulas, and any clause that's implied by them you can use. So you don't even have to worry about this. But anyway, we'll use just soundness. So I want to show you how. And what do we want to prove? We want to prove that there is a large clause in every proof of phi. So we'll assume that we have some proof. We have some C1, C2, CT, which is the contradiction, is a proof of phi. So this is A1 and AM, and the rest are derived according to a sound rule, as long as there are clauses. And we want to prove that one of these clauses must have many variables, linear in R, the constant times R. So we're going to do it indirectly. We'll first prove that something about some clause is large, and then we'll use it to conclude that actually its length is R. So we are going to define first a progress measure on proof systems, so mu. And mu is going to take, it's mu of Ci. So some progress measure. You'll see in what sense it's a progress measure. On the proof, it will be simply the smallest number of axioms that are used to derive this clause, right? So when we look at some clause here, Ci, we can trace back. We just open the resolution proof and we see what leaves we reach, which axioms were used in derive. What? Yeah, it is right. So it's simply the size I such that, or the minimal such size such that AI, let me write it like this, capital I, implies CI, is the axioms that are used to derive CI. You can define it according to the proof. You can define the minimum of it. So it can be either the specific axioms that are used in the proof to derive I, or the minimum number that you use it. Both will work. So what's good about this? In what sense is a progress measure? First of all, for every axiom, is 1. Right? It's small in the beginning. It's large at the end. Why do we know that? Because of robustness, right? Yeah. So this robustness. So it starts small, it's large at the end, like a good progress measure. We also want it to grow slowly along the proof, and it's obvious that mu, so if we derive Cj, Ck, we're used to derive Ci in the proof, in the given proof pi, then mu of Ci is at most mu of Cj plus mu of Ck. Okay? Right? I mean, because we look at what these two subtrees reach and take their union. Okay, so this is obvious, and what are we going to conclude from this? That there must be a clause with intermediate mu value. So, conclusion, just from the fact that it's a progress measure, there exists an I, so that mu in, well, let me write it like this, Ci in pi, in the given proof, so that mu of Ci is R over 3 to R over 3. There's the one with large value, but not large all the way up. This is just for, yeah, anyway. You need such a bound. And, okay. Now what do we do? So now we want to prove, so we already know that this progress measure is large. Now we want to show that the closed size is large. And there's only one thing we didn't use, the expansion, right? We used robustness already, we didn't use, so we are going to use expansion, obviously. So you're going to say the following. Well, look at I, this set of, so suppose that AI implied Ci and i's in this range. So in particular, it's at most R, right? So we know the expansion. So we know that, so this set, the set, I know AI1, AI, no, T, so this equals T, oh not T, L. So there are some axioms that were used to derive this clause. And I want to claim that this clause must be large. How do I know that it's large? I know that the boundary of this set, so there are these sets SI1 to SIL, which are the supports of these axioms. And I know that the boundary is large. What does it mean the boundary is large? There are variables that appear in exactly one of these and don't appear in the others. Now you tell me, how can a resolution proof eliminate a variable that appears in only one axiom? If there is a variable that appears in exactly one axiom, nothing can cancel it. To cancel it, you have to has to appear. So this implies, so expansion implies that Ci is at least a constant. And because we have a lower bound of R over 3, we get that this. Yeah?
In every one is participating, you should also.
Yeah, so we took a minimal set of axioms. It's important. It's minimal. It can be either in the proof or in general, but it's a minimal set of axioms.
There is a small issue with the citing because you take every equation and you.
There is no issue.
Each variable does not appear.
Well, first of all, one way to do it is really expand it to clauses and take only the clauses you need.
Okay, but then it's not really.
Yeah, but you're right, and it's a very good point. In fact, you have to actually look at these equations as, so you don't want the repetition. What you're saying is this will be really bad if we have equal rows in this matrix. You cannot generate unique. So actually what you do is really think of them as arbitrary functions, and you coalesce them. So you really use the linear equations. In the proof, as we said, you are allowed to use any sound deduction, so you can deduce from this any clause you want. But when we count expansion, we look at the equations. There's similar technicalities happening with the pigeonhole principle. It turns out that to look at these axioms and you don't want to look at these axioms. I'm not going to explain what you do. These are technicalities and they are simple. Citing is the most elegant, or maybe this is the most elegant. This is just a random hypergraph. I didn't prove it, but it's obvious that you take not too many. Let's say you take at most n over 10 random 3 subsets, and there will be many things that will occur just once. A linear number of things that will occur only once. So that's the simplest. And here you need to do these technicalities. But anyway, we get a constant times r lower bound. We are done. And in all of these, r is linear in n, so you get the exponential lower bounds. Okay? Questions about this before I move? Yeah.
So, from what you were saying, you can't really hope to generalize the, I don't know, Sutin or something or other.
Citing.
Citing.
Citing, yeah. A Russian guy.
That, tautology language, by sort of allowing some kind of polynomial equations. I mean, as opposed to your linear equations.
You can, and people, so, you mean for resolution?
Yeah.
Yeah, but for polynomial calculus.
Yes.
For polynomial calculus, you can, and it turns out that people did it, and there are lower bounds for polynomial calculus, which, they prove lower bounds on degree, and degree lower bounds for polynomial calculus are the analog of width lower bound in resolution. Yeah. And citing tautologies is actually a very friendly, unlike pigeonhole principle, it's a very friendly tautology to prove lower bounds for polynomial calculus. But I'm not going to go into this. Okay, so we are done. We proved 3 theorems. Now I want to go to feasible interpolation. I owe you the width theorem. Yeah, that's what you want to see. Short proofs are narrow, so let me show you this. And then we go to the feasible interpolation. So I'll show you the first one. Again, it's really simple. There's a clever trick, but it's a simple proof. So what do? take your resolution. We are given some resolution proof of size S, tree-like resolution proof of size S. How does it look? There's a, we derive the empty clause from something, from some variable. Okay. And then, there are. So this is, let's call it, so this is pi, and pi is of length S. So let's call this pi 1 and pi 0. It's actually better to call this pi 0 and this pi 1. Right, that's how a tree-like resolution proof looks like. There's no loss of generality here, and moreover, because it's a tree, I can assume that this at most S over 2, right? So now I want to do, so the proof is by induction on 2 parameters. One is S, and the other is N, the number of variables. So again, I'm cheating somewhat. I'm not taking the width of the initial clauses into account. They are a constant, and you can add here a constant. I mean, in both cases, what you really need. Just for the basis of the induction, but I'm going to ignore that. So what is the idea? The idea is that we want to use, so it will be induction on N and on S. So here we can use induction on S. We have a much smaller subtree, but it's not proving the empty clause. When we talk about proofs, we talk about proofs proving the empty clause. That's resolution proofs for us. Of course, we can generalize it. We can talk about the shortest resolution proof yielding some clause, in particular yielding some variable. But what you can see is that if we look at, so there are some clauses here. So if we look at phi and set x to 0, then here we have a resolution proof. So x fell from there. Some axioms fell and some clauses containing x fell. And then these sub axioms are proving is a resolution proof. We prove a contradiction, right? So pi 0 proves, so pi 0 can be viewed as proving this statement, right? And pi 0 is of length S over 2, so we know that the width of this is at most log S minus 1, right? Just by induction. Okay? You look like it's okay, Gilad.
So phi x equals 0 is a contradiction too?
Yeah, of course. When you any partial assignment to the variables in a contradiction is a contradiction. So it's a contradiction, and it actually has a proof here, a tree-like proof here. So we can use it, and we know that. So we also know that the width of phi. Yeah. So.
Maybe you should set to replace, like, syntactically every place you have CJ, CK by CI, you can replace it with CJ.
Yeah, but I'm not going to say it's so there are details. Yeah, it is simple. I don't want to write it down. The proof of this is simple. So what do we infer from this? I want to infer that there's a pi, let me call it pi 0 prime of width, now of width exactly log S, at most log S, such that pi 0 prime proves x. So I use induction, I get a proof, a contradiction proof for this of width log S minus 1, and then I put x back. It was an empty clause at the end, I'll get x back. Either x or already the contradiction, in which case I will be done. So I can derive x using a proof of width at most log S. This is the bound I want to prove, right? Now what am I going to do with it? First, let's look at the right-hand side, and I want to use induction on n here. Let me note that phi when x equals 1, so I can set x to 1. I have here a proof of length at most s, but on one variable less, so I know that this is at most log s. So there exists a proof pi 1 prime of width. So now I can put x back into these axioms of width at most log s, such that pi 1 prime proves x bar.
Plus 1, right? With
No, not plus 1.
if you put
So sorry. No, I don't. Yeah. Just of this statement. Of this statement. Of phi x equals 1. Sorry. Not. I'm not adding it back. Sorry. So what's the final trick? Maybe you see it. So I have here pi 1 prime, which proves the contradiction, but I don't have the axioms of pi 1 prime. However, I have this. I have this thing which generates x. Right? So I can apply. So for every place where I have something x, something x, some clauses with x, I simply plug here pi 0 prime. And it generates the x for me. Right? So I start from my original axioms. I'm generating these clauses. So I have the clauses phi x equal 1, but I put the x back effortlessly. I mean in width log s. So width log s here, width log s here, and we get a contradiction.
What if you have not x in the bottom? What do you do?
No, I don't. I mean, that's exactly... Well, not x will kill the clause. I don't need to... I don't need this. I simply don't use them, right? Because this thing generates x bar, when I put x equals 1, that's all I need. I need only clauses in which x equals 1, right? Without loss of, I mean, when you are deriving x bar, you are never going to use clauses containing.
No.
Did I?
So the assignment has to contain x bar.
No, x bar, I'm sorry, x bar. I'm going to, I didn't say it right. I take the clauses, I take the original clauses of pi 1 prime. Yeah, I took, and then, and what, and exactly, so I didn't say it right, I'm sorry, let me say it again.
So is it pi 1 prime or pi 1?
No, I want something that has that is narrow. So I want something with the width of this pi 1 prime is at most log s.
Okay.
But the problem is that I have here clauses in which there is something, or I wanted this in the assumption here. The question is, where do I take this assumption? I don't have this set of axioms, but I claim I do. How do I do it? Whenever there was a clause like this, I put here the whatever thing pi 0 prime which generates x, and I take a resolution proof, so let's call it, I don't know, d or x, and I get d. So all the axioms that I use in pi 1 prime, which generates this, I can get using plugging in this low width proof for x, which I resolve against this x bar, and I get rid of it.
Okay. Yeah.
Okay?
Very nice.
Okay. What happens in this case? Well, in this case, what did we actually do? So this sort of captures the restrictions that are actually going in the various proofs, and they are using random restrictions, starting from Haken. You see that we restrict a variable and in some sense use induction on the things that contained it, and for some variable, the set of clauses we need to look at went down by a factor of 2. Now, in general proof, in general resolution proofs, we don't have this luxury of this partition of the proof to 2 parts, to disjoint parts. But you argue roughly as follows. I'm not going to write anything down. I'm just going to tell you where this is coming from. At least I'll tell you where what this would be coming from. Square root n times the whole of log s, but I mean, you can do it this way. So we want to kill all the large clauses. That's what happened here. You say if the proof is short, we can generate another proof without all the long clauses. So now we are given a short proof, a general resolution proof, not a tree-like proof. And it has some clauses bigger than root n. It has some clauses smaller than root n. Those that are smaller, we don't care about. I mean, we are going to generate a resolution proof of roughly of width log n. Those that are bigger, we know that because each of them is at least root n, we know there must be a variable that it appears in at least a fraction 1 over root n of them, right? So we are going to kill not half the proof, or take care not of half the proof, but take care of fraction 1 over root n. We will need to do it root n times to kill a half, and then another log s times to kill everything. So that's what we do. We do exactly the same trick, but each time we apply the induction, we go down not to size s over 2, but we go down to size s times 1 minus 1 over root n. So that's the only difference. You can figure out the details. It's not complicated. So the last thing I want to do is tell you a little bit about the interpolation property and the feasible interpolation property for resolution. And the lower bound for the click versus coloring contradiction. I'm erasing the progress measure. The same idea with progress measures can be used to prove lower bounds for other proof systems, and the Schoenebeck lower bound for the sum of squares hierarchy uses follows the same ideas. So you can prove degree lower bounds this way. Okay, so I want to talk about feasible interpolation. So we said that we don't know if a resolution is fully automatizable, but it's fully feasibly interpolable. So the theorem, as I said, of Krajicek and Pudlak, Krajicek and Razborov independently, is that if we have phi, which is phi 0 of x and z, and phi 1 of y and z, and we have a resolution proof, and pi is a resolution proof of phi, then if we are given this proof, maybe I didn't, when I stated the interpolation property, I probably didn't state that the proof is given. So the feasible interpolation is a problem of determining which of these two parts must be a contradiction. This is a contradiction. So we are given a proof of phi, and then, so there's this algorithm, polytime algorithm B, so for every such formula, and with a resolution proof, B of phi pi determines which of phi 0, phi 1 is a contradiction.
For a specific z naught, right?
Sorry, and which of them is a contradiction? Thanks. Right. What is the idea of the proof? The idea of the proof is that there is only one thing to do. So why did I do this in a stupid way? As you pointed out, there was a much simpler way to get a contradiction. But I tried on purpose to do what Gilad suggested, that maybe there is a proof which involves them and then at the end unravels them. Even though that, so here is, this is phi 0, this is phi 1. This is in x, this is in y, right? And I tried the first step here to involve, a clause of x's and a clause of y's. But now notice you are given a z0, an assignment to the z's. Once you get an assignment to the z's, the first thing, so you are the algorithm B. You are given this proof pi. And you want to determine which of the, phi 0, phi 1 were contradictions. What are you going to do? I mean, first you substitute z into the axioms. What does it do? For some axioms, it kills them completely. For others, it just removes some variables from the clauses. So let's, for example, do it here. If z0, which is now one variable, is 1, what happens? This becomes 1. This becomes 1. These are useless. Axioms which are 1 are not helpful to deriving 0, a contradiction. And this becomes y, and this becomes y bar. But basically, what you see is that the axioms partition into two sets, those containing only x's and those containing only y's. And then you start following the deductions in the proof. I mean, deductions can either use x variables or y variables or z variables. There are no z variables anymore. So there will never be, you can start eliminating things that are redundant like this, because this doesn't exist, this is just 1. So you can remove, so ones propagate to ones, so ones are not interesting clauses. Basically what you see, because resolution occurs only between x variables and themselves or y variables and themselves, is that you'll get a disconnected graph here. There'll be things that will follow from the y's, and there'll be things that will follow from the x's, right? It will be disconnected because they never talk to each other. Before they talk using the z variables, they don't talk to each other anymore, right? So there'll be two disconnected graphs, and in one of them, you will reach, because you can reach the empty clause here with restrictions, you'll reach the empty clause, well, here or earlier. So you'll just see a polynomial time algorithm for this, given the proof is obvious. I'm not going to explain it more, but what's important in this observation is that it goes quite a bit farther. So any questions about this? I mean, it's really as simple as it gets.
So it's disconnected because every time we connected them, we used z and we couldn't use it?
So let's see, z0 equals 1 means that, this, yeah, basically you start labeling the clauses as being either x clauses or y clauses or just constant 1 clauses which you can throw away, right? This becomes, because this is a constant 1, this is a constant 1, so, so anyway, you erase, you basically erase the x here. So you're resolving 1 with a clause. This was 0, then this becomes a y. Right? So you start erasing things. So this becomes a y. And this becomes, here it becomes, well, I guess this will become y bar. Yeah, the x variables all fell because Z killed them. No, it's not a bit. It's the same simplicity in the general case. And so,
Resolution proof of the restriction.
what?
Right, from your original resolution proof, you're getting a resolution.
Yes, but the point. But what does it mean? A resolution proof of the restriction? Does it follow from the x variables? We are asking ourselves which is a contradictory set of axioms? Those with the x variables or those with the y variables? It can be a different set depending on the assignment to Z.
Yeah, it's just that for any resolution proof, right, if you restrict the value of a variable, then
Yeah.
mechanical sort of linear time way, you're getting a resolution
Absolutely.
proof of the restriction.
Of the restriction. And the additional observation is that the resolution proof of the restriction is either a resolution proof of the x's or of the y's, and you can tell because the two parts are disjoint. They are disconnected. So you can tell which one. If we made z0 equals 0, then you will get a contradiction in the x. So it's really simple. I mean, you're right, it's very simple, but it's simple in general. So the point is, though, that this is that's just the beginning. This is just a polynomial time algorithm. But it turns out that what they proved is more. In fact, if we have, in fact, so two things. You can make B of Z a circuit of size, linear or anyway polynomial in pi. So this is an algorithm. You can make it a circuit where it's obvious you can take an algorithm into a circuit, but it's more than that. You can more or less syntactically replace the resolution, the places where resolution happens with the constant size circuit with ends and all. So in fact, you can get it a circuit, and in fact, or additionally, that's if phi 0 contains only Z and phi 1 contains only occurrences. So all the occurrences of Z appears positively in phi 0 and negatively in Z1, in phi 1, then B is a monotone circuit. So this circuit, which takes just Z values, is a monotone circuit. Okay, so that's a very important observation. Why? I mean, we are going to prove a lower bound for the clique versus coloring tautology by reducing it to proving monotone circuit lower bounds for clique versus coloring. If we had to reduce it to proving circuit lower bounds for clique versus coloring or for anything else, we would be like that, because we don't have any non-trivial circuit lower bounds, general circuit lower bounds, right? Still, I want to point out that it would be extremely interesting to get proof complexity lower bounds relying on some circuit lower bounds which we don't know, just assume. So it would be extremely interesting to show that if P, if NP does not have polynomial size circuits, then there are super polynomial lower bounds for Frege. It would be extremely interesting. It's a great open problem, and we don't know it. I mentioned last week that we don't know any Frege lower bounds, and I don't see any reason why we don't. But even conditional of having, clique requires super polynomial size circuits. Assume that. We don't know how to prove Frege lower bounds. So that's extremely interesting. But anyway, we know this additional fact. So now let me remind you of the clique versus coloring tautology. I'm not going to write it completely in full, but it's a very simple thing. So what is clique versus coloring. So we have a graph G and a parameter K. So it says that phi 0 is going to say of x and z. So this will be encoded by the variable z. And phi of x z will say that x is a k click. So x variables encode the k click in the graph z. And phi 1 will say that y is a k minus 1 legal coloring of z. Okay? And you can make this encoding such a way that it will satisfy this property. So I showed it last time. Let me not show it again. I mean, there is a very simple encoding that will allow you to do that. So so basically from this we get that size S resolution proof of click versus coloring implies monotone circuit. What does a monotone circuit do? It tells us which one of them is a contradiction. Right? They cannot be true. Every fixed graph cannot have both k minus 1 coloring and a click. So which one of them does not hold? So it should. So it basically tells us if we have the promise that the input graph either is a k click or a k minus 1 coloring. Right? These are what the graph itself is fully a k click or fully complete k minus 1 partite graph. It will tell us, the monotone circuit will tell us which is the case. Okay? So there's a monotone circuit of size S as distinguishing graphs Z which are, well, let me call it G. Well, let's see. C of Z. Distinguishing Z which are k minus 1 colorings, k minus 1 full k minus 1 partite graphs or k clicks.
The monotone circuit either says that there's no k click or says that there's
Yeah, so let me put a complement. And so it's a monotone circuit. It gets a binary string, which are the adjacency matrix of a graph. And let's assume, so all we want is that if the graph itself is a k click, it will say 1. And if the graph is a complement of a complete k minus 1 coloring, it will say 0. That's implied by what we want here. Okay. So if we had the proof, then we would have such a circuit. And luckily, Razborov's lower bound for the click, for monotone circuits and click, is much stronger than it was before. So one might even, I mean, when monotone circuit lower bounds came on stage, well, you can say, who cares about monotone circuits? Well, but we cared because for 40 years we couldn't prove lower bounds even for monotone circuits. So finally, Razborov did it. But you can still ask what's the value of monotone. It's okay, we develop techniques and so on, but is it of any consequence? With nobody, restricts us when we are coming to solve the click problem to work with monotone circuits. So this implication is, I think, is an amazing demonstration of how monotone lower bounds can be useful to a problem that has nothing to do with monotonicity. The resolution proof system certainly works with negated variables. Right, and nevertheless because of this, requires exponential size here. So I'll just remind you of the results. So theorem, Razborov did not prove exponential lower bounds. Alon Bopana did it. They improved they did a more careful argument. S below is at least exponential in 218. So there is an exponential lower bound on circuits, even if their input is solely, graphs which are cliques, or solely graphs which are the complement of k-1 partite graphs. If they distinguish the two, then they have to be of exponential size. So it's exactly the lower bound that we need there. I don't know how many people realize this, so let me just end with a question. So is this problem just a problem of distinguishing k-cliques and k-1 colorings? Is it easy or hard if you are not restricted to monotone circuits? It's extremely easy, yeah. So why?
Just count edges or something.
Yeah, so very good. That's really good because it's really easy because you can count edges. Now suppose I make it harder for you. I give you a graph, and what do I promise you? Yeah, I want you to answer yes if the graph contains a k-clique, to answer no if it contains a k-1, if it has a legal k-1 coloring, and do anything you want otherwise. It doesn't have to be both, right? They are not. Yeah. So is this problem easy or hard?
Can you repeat the problem?
The problem is even G say yes if G has a k-clique, no coloring, and anything otherwise. What's the complexity of this problem? You should know. Somebody should know. So this is in P. This is an observation of Eva Tardos. I'll tell you why in a second, but it gives an example of a problem for which there is a polynomial size circuit, but every monotone problem for which there is a polynomial size circuit, but every monotone circuit for this problem requires exponential size. So, last chance. Why is this true? Well, anybody remembers the Lovász theta function? So the Lovász theta function is a parameter of graphs that can be computed by semi-definite programming, and it's sandwiched by the clique number and the chromatic number. Okay, questions?